All right. So what we usually do in the classroom is we run a little experiment at this point, and I want to show that to you here on the left side. So I will draw a bathroom scale that I usually bring into the classroom, and I asked one student to step on it. And that student, of course, shouldn't be afraid of giving away his or her weight. And the last time we did this in the classroom, I had a student that actually measured 170 pounds. So 170 pounds were measured by the scale. Then I bring a second scale and I ask the student to verify that the weight is really properly measured with the 170 pounds. And I ask the student to also step on that one so that we can use both scales equally. And what we find there is that the student still has a weight of 170 pounds. While my bathroom scales are not always super accurate, they are accurate enough in this situation to actually measure the same numbers here. So why do I need them to be accurate? Because next I will ask the student actually to step on the two scales in a different way. So let me copy these bathroom scales here. One I put here and then the next one I put right next to it. And what I do then, I ask the student actually to step on each scale with 1 foot. And I ask a second student to come in and report to us the real numbers. So 1 foot is here and 1 foot is there. And now think about what happens. We usually have a slight disagreement about this in the classroom, but usually we agree to it afterwards. And I want you to think about where the disagreement could be. So what do you think these bathroom scales would read right now? Exactly. Each one of them would read the same number and they both would read 85 pounds. So the left one would read 85 pounds and the right one would read the very same. And this has something to do with force equilibrium. Sometimes students think because if you stand on a scale, you have to actually spread your legs, right? So you have your left foot on this scale and the right foot on this one. So therefore you think that there's a force component that kind of pushes more, or at least that's what some students think. But at the end, if this is F student, then of course here you have F student over 2 and here you have F student over 2 as well. And so we can usually agree on that for this concept. But then comes the next part where I kind of repeat the experiment, but in this case I move the scales a little bit further apart. So let's move one scale right here and then the second one I move, let's say, 1 foot apart from one another. So I usually bring in my tape measure and measure that the distance here is really 1 foot. And then of course again I ask the student to use one scale under each foot. So that looks like this. So now we have the student standing on there, and then I ask the other student again to read what the scales tell us. And yes, you guessed it, for the very same reason that is true here, even if you spread the legs further, of course, you have to read the same number. So we have 75 pounds here and we have 75 pounds here. And that should make sense in a general context. So last but not least, I asked the student this one more time to actually put one scale right here and then the second scale very far apart. In fact, I usually bring in my tape measure and make sure that they are actually 60-inch apart from each other. And then the student looks at me funny and says, hey, I'm not on the cheerleader team, I cannot do that. So we need to break off the experiment. But I say, no, don't worry. We can actually make this work because I then usually bring in a rigid body, and the rigid body comes in the form of a wooden beam that I put on the scale. So let's draw the wooden beam on here. That looks something like this from the top. And I use some spreader beams underneath it to make sure that the load is properly introduced into the scale so that we can get accurate readings. Another thing that I do actually is I make sure that I now zero the scales. So now I actually make this a 0 reading, so 0, and I also make this a 0 reading before the student actually steps on it. And then I ask the student to step at the center mark, so put 1 foot here and 1 foot there. And then I asked the rest of the class what happens now to the readings of the scales. And I let them think a little bit about it, and then we move to this table here. So let's go ahead and put the student actually on the simply supported beam that you see here that idealizes my structure. So I have a force here with 170 pounds last time we did it in the classroom. And then I have a distance of 30" here and a 30" distance here. Please take a look real quick. The simply supported beam or the rigid body I actually idealized with the solid and the dashed line here. I will talk more about this later on throughout the lecture, but from now on just understand that it's not a cable, it's a rigid body, and a rigid body always has what we call a reference fiber here, the dashed line underneath, so you always need to include that. And what you will calculate later on is what is always called here in this case RAY. So R for reaction, A as point A, and then Y in the Y direction. Therefore, here on the right side, I call this RBY. R for reaction, B at location B, and Y in the Y direction. So these are obviously the scale readings. So this is equal to the scale. And this is the left scale and then the right scale. So let's take a look at the numbers that I last time collected actually in the classroom. So I will now present to you the numbers that we measured in the classroom. And there is some imprecision here, so don't get confused about that. That's just because my equipment as a bathroom scale is not real engineering equipment, but it gets the point across. So we measured 90 pounds on the left scale and we measured 80 pounds on the right scale. And you can see on the very far right, we totaled it for each of our measurements. And in this case, we ended up with 170 pounds. Now, that is not a surprise because it's a symmetric system and students would have guessed that. But then I asked the student to actually step on the 20" mark, which let's pretend is right here. So now the student with 170 pounds steps there. We have 20" right here. And that leaves us with 40" right here. And then I asked the student to guess what happens before the second student actually gives us the scale readings. So go ahead and think about what you would answer in the classroom if I would ask you in this scenario what the left scale and the right scale would read. All right, now that you thought about that, my next question in the classroom would be, hey, which one of the two support reactions, RAY or RBY, would be larger? And I want you to pay close attention to this because when I ask you this, it's very clear to you, but sometimes in exams, it's not that clear. But if you really think about it, you probably would say that this needs to be larger than it was before, and this one needs to be smaller compared to this scenario. Why? Because the 170 pounds moved closer to this support and further away from this one. And in fact, when we recorded it in the classroom, we actually found that the left support now measured 112 pounds, whereas the right side measured 58 pounds. And while this is not super precise numbers, they still totaled up to 170, which was a good thing for us to find. All right, next I asked the student then to move to 40" mark. So let's put the student on the 40" mark, which let's pretend is right here. So there would be the 170 pounds right there. That leaves this with 40" and then this with 20". And we obtained measurements for that as well. Of course, you already understand that now this support on the right side needs to become larger. In fact, it needs to be larger than even it was up here. Whereas the one on the left side needs to be lower. And if you pay closely attention, you already see that it's effectively the same system as this one, just flipped around. So you should kind of see the same numbers again. But when we measured it in the classroom, we ended up with slightly different numbers, which was 57 and 113, but again, a total of 170. Then the student is asked to step on the 50-inch mark. So let's put the student right there with the 170 pounds. 170, which leaves us with 10-inch here and 50-inch here. And now, if you already think in your head, hey, I clearly understand this concept, which hopefully you do, spend 3 seconds, 5 seconds before you continue the video and ask yourself if you could predict what numbers we measured here in the classroom. So go ahead and do that, and here we go. All right, so you probably agree with me that this force now needs to be larger than this one. So the right scale needs to be even more than 113, but certainly it needs to be less than 170, right? So you could at least approximate it. But if you already understand the concept, then you could even calculate it precisely. I'm not doing that yet. I will do that in a little bit. But you would find that the right scale in the classroom actually read 142 pounds. And then we had 31 pounds on the left side. And you will find that this sums up to 173, which again is due to the imprecision of our equipment, but the physics is still true. So technically there's some error in here and some error in here. It should be 170 as well. So let's just pretend that this here is roughly 170. Last but not least, I asked the student then to step on the 60-inch mark. So that the student would be standing here, and then we had 60-inch right here. And yes, you absolutely guessed it. There is a 0 here and then a 170 here for a total of 170. And 2 very important things to take away from this table. Number 1, what comes up has to come down at some point. So this is effectively equilibrium in the vertical direction. So you can say the sum of the forces in the vertical must be equal to 0. That is the first thing we take away from this. And then the second thing we take away from this is the closer the force moves to the support, right? The closer it moves to a particular support, the larger the number will become until it hits the maximum here in this case. And likewise, the further away the force is from the support, the less force you will find in this type of support. In fact, you might see a relationship between the geometry of these problems and the scale that, in fact, you might see a relationship between the geometry of these arrangements and the scale readings that were returned to us in the classroom. And if you do not see that, please try to think about this for a second. So I'm going to move on in a second, but please pause the video and try to find a relationship between the geometry and these numbers. That is something that I will explain further down the road. But for now, let's just remember that from this table, the 2 things we can learn is everything that goes up has to come down. And the closer you come, the more force you support. All right, so with that said, we can now move on and take a very specific example out of the table. And the one that I want to pick is where the force was actually sitting at the 40-inch mark. So I draw my seemingly free body here, and I had a support reaction RAY here. I had another support reaction here RBY, and I picked the case where my force was sitting at 40-inch with 170 pounds, so that the geometry looks as follows. I had 40-inch right here and 20-inch right there. And now the question is, why are the numbers as they are? And you may already have guessed it, or you may already have seen that in the table. There is a relationship between the geometry and the numbers that the scale gave us, but the question is why, right? So if you want to try something, it doesn't hurt to write down the sum of the forces in the y direction being equal to 0. and usually upwards positive, right? So therefore 0 would be equal to plus RAY plus RBY. And by the way, I always start my equations with my unknowns, and here I have two unknowns, and then minus 170 pounds. So notice that I have one equation with two unknowns, so I cannot solve this. I mean, it's a good thing to write down because it definitely helps you to understand the physics of the problem, but I obviously cannot solve this because I have two unknowns in the same equation. So the question then is, what can I do next to find RAY and RBY? And then, of course, the students say, hey, we have a second equation usually, but the second equation would be sum of the forces in the x direction is equal to 0. And in this case, we have nothing that acts in the 0 direction or in the x direction, so therefore x does not even exist. So what do we do now? Like, why does physics still work? And the answer is we have one more equilibrium or one more concept that we have not explored yet, and that is actually moment equilibrium, right? So moment equilibrium. So far, the only thing we have done with moments is we calculated moments, like we called it acting moments, but now we want to use the moment to actually find the answer for our support reactions. So I asked the students in the classroom to apply moment equilibrium to the system without any further guidance. And so what we usually end up with then is an equation that says, hey, why don't we just take the sum of the moments about, let's call this here point C, about point C. And of course, we'll take counterclockwise positive, and we say that's equal to 0. And then the equation will read what? 0 is equal to RAY multiplied by 40 inch. And we also have RBY, which has a lever arm of 20 inch about that point, but now we need a directional sense. So RAY turns clockwise, which makes it negative if we turn about this point, and RBY, which turns also about this point, would rotate counterclockwise, and that makes it positive. So let me assign those signs here. And now I can actually state, hey, I have equation 1 up here, and I have equation 2 right here. And I could now solve two equations with two unknowns. So this can be solved, and this is a valid way of dealing with these type of problems. But there's obviously a smarter way or a easier way, and engineers like to work less, I guess. So therefore, we need to find a way to reduce our calculation effort. Don't get me wrong, mathematically, this is obviously super easy, but maybe we can make our life even easier. And so what do we notice in this equation number 2? We notice that 170 was not part of the equation because we would have a lever arm of 0, right? And so why can I not change the location to turn one of these into 0? So for example, if I take the sum of the moments about point B, then this one would disappear. If I take the sum of the moments about point A, then A would disappear, or RA would disappear. And so if I want to calculate RAY, what I really would be doing as an engineer, I would take the sum of the moments about point B being equal to 0, counterclockwise positive, and then I can say 0 is equal to, let's say, RAY, I always start with my unknown, still turns clockwise, so negative, and has a lever arm of 60. So minus RAY multiplied by 60 inch. And then I have my 170 pounds multiplied by 20 inch. And this one turns actually, let's see, it turns counterclockwise, so therefore it is positive. All right, and now I can solve this equation, right? So RBY is not even part of it. So I now solve the equation for RAY, which is equal to 170 pounds divided by 60 multiplied by 20. These are 2 inches. Both of them are inches, I should say. And so we actually have 170 pounds times 1/3. And if I calculate that, out, it would come out to be 56.66 pounds. And that is very close to what we found in the table up here, right? So we actually found that we have 56 in this case, or I guess we actually should flip this around. We actually looked at this case here, so 57. So 57 is very close to what we found here. And the reason why the scales measured this is not just force equilibrium, but it's also moment equilibrium. And let me talk a little bit more about moment equilibrium and why we need support reactions. So the reason we need support reactions is we need to prevent this entire system, this rigid body here, which you can think of as a bridge, we need to prevent it from falling down, we need to prevent it from moving left and right, but we also need it to prevent rotation. So this rigid body cannot rotate. So just like the force equilibrium prevents a system from falling down or going up, rotational equilibrium prevents a system from rotating clockwise or counterclockwise. So we could use this equation here to state that this is in static equilibrium, it does not rotate, therefore the sum of the moments is equal to 0, and therefore we were able to solve it using this equation. And that's why we actually found what the table suggested, or what the scales suggested in the classroom. We found the very same answer with the very same relationship. For completeness reasons, let's go ahead and actually also calculate RBY using this method, just so that you can see how it applies and so that you can verify your results. So let's go ahead and find the equation for RBY, which we would do by the sum of the moments about A in this case is equal to 0, and that is also counterclockwise positive, and then 0 would be equal to RBY multiplied by 60 inch, and this in this case would rotate counterclockwise, so therefore it's positive. And now the 170 rotates clockwise, so I multiply that by negative 170 pounds and by 20. No, that's not true. It's not 20. It's actually 40 inch in this case, right? It must be the inverse. So therefore, I can now calculate my numbers. So my RBY is equal to 170 pounds times 40 divided by 60, which then comes out to be 113.33 pounds. So that once again is what we found in our result table, and it's not a surprise that I can now go back to my initial equation here, the sum of the forces in the y direction, and if I plug in RAY with 56 and RBY with 113, then this will be equal to 0. So I might as well check that one off. So check. So that is actually what engineers do in the real world when they, let's say, have to calculate the bridge based on like a truck that's driving over or something like that. They use the moment equilibrium for finding one of the support reactions. Then they use the second moment equilibrium equation to find the other ones. And then they use this formula here, the sum of the forces in the y direction, to check. Right? So obviously it's tempting to use this formula and then plug the value back in here, which is acceptable. But I would recommend that you use these two approaches to then check your value here at the end. But we'll talk more about that when we solve actual examples. What we need to understand here is that we used the sum of the moments about point B, so about this point, to make RBY disappear from our moment equation as we had it set up here before. That was one thing we need to understand. And then the other thing is we need to understand that the rotational sense, right? So the rotational sense that we define here really defines the science here. Sometimes students are very tempted to define a negative and a positive based on the direction. So for example, here RBY goes up, therefore it's positive. RAY goes up, therefore it's positive. No, this goes out of the window now. It's only dependent on the rotational sense. And that's why RAY here is actually negative, and it rotates clockwise. Therefore, it's negative, right? Remember the right-hand rule. That's where it's coming from. And probably more obvious this will become when you look at the 170 here. Because here, because you rotate about B, it's positive, right? So you have this force times this lever arm. So it's a positive rotation. Whereas here, in this equation down here, RBY, it actually becomes a negative rotation because it turns clockwise about this point. And so please do not fall into the trap of following the direction of the arrow. Some people would say, hey, 170 points downwards, therefore it's negative. And that's what you see here, but that is not the full story, right? The negative does not come from the fact that the 170 is pointing downwards. The negative only comes from the fact that the 170 rotates clockwise about point A. And that is an important concept to understand. But I think we now understand where these numbers come from and how equilibrium works, in a sense that we can use rotation as well for equilibrium condition. And that is what engineers use to really calculate the support reactions of, let's say, a bridge. And with that said, we now have a general understanding of where support reactions are. We now understand how we can calculate them. So the last thing I want to do for you is to define the differences between the different support reactions. So later on, you will not see the pictures anymore like this here with the arrow up and the arrow up here. We actually have symbols that represent specific support reactions, and I will now define those for you.